Hi there, and welcome to our lecture on reaction rates and equilibrium. This is reaction 4 of Unit 4. Our key ideas. What kinds of things speed up a reaction? What does a catalyst do? And what happens when a reaction goes backward as well as forward? So, start looking at this first question. What kind of things speed up reaction? Anything that increases contact between particles will increase the rate of reaction. For any reaction to occur, the particles of reactants must collide with one another. So we have to find a way to make those collisions occur more frequently for a reaction to speed up. Most reactions go faster at higher temperatures. So therefore, temperature will increase the reaction rate, will increase the reactions. A large surface area speeds up reactions. So the more surface area that a molecule or particle has, the more likely a reaction is to occur. If we have higher concentrations, if there's more of a particular substance in solution, then our reactions are likely to go faster. If we increase the pressure, so when we increase the pressure, we're decreasing the volume. That means the particles are getting closer together, so reactions will go faster or speed up. On contrary, if a particle is more massive, it's going to react more slowly than a smaller particle because it doesn't move around as easily, so it's a little bit slower to move, a little bit slower to react.
The speed or rate of a reaction depends on several different factors. Some reactants tend to react more than others. In this chemical reaction, silver is much less reactive than copper. Increased surface area tends to increase the rate of reaction. When wood burns, a reaction occurs between the wood and the oxygen in the air. The larger the area where oxygen can contact the wood, the more rapidly the wood will burn. Increased temperature tends to increase the rate of reaction. Increased concentration tends to increase the rate of reaction. When we increase the concentration of hydrochloric acid, it increases the number of chloride ions present and decreases the distance between them. The presence of catalysts and enzymes in some cases can also increase the rate of reaction. For example, the decomposition of hydrogen peroxide into water and oxygen is very slow unless a catalyst such as manganese dioxide is used.
Alright, so looking at a catalyst, what does a catalyst do? A catalyst can speed up or slow down a reaction, but it is not changed or affected by the reaction itself. So we can recover the catalyst after reaction takes place if we need to. So to define catalyst, a substance that changes the rate of chemical reaction without being consumed or changed significantly. An inhibitor is a type of catalyst, but an inhibitor is just the one that slows the reaction down. Still a type of catalysts. And typically we use catalysts in industry to make reactions go faster. It saves time and money if we can make reactions go faster when producing or creating a product.
A catalyst speeds up a chemical reaction by lowering the activation energy. The catalyst is not consumed during reaction and can be reused. Catalysts are often shown above the arrow when writing a chemical equation. Enzymes are proteins which act as catalysts for chemical reactions. Their shapes are specific to certain reactants and fit like a lock and a key. In this case, the enzyme flexes, causing bonds in the substrate to weaken and the molecule to split apart. In other cases, the enzyme may act as a catalyst by bringing two substrates into proximity so that a chemical reaction can take place.
So enzymes are just special types of catalysts, and specifically they are catalysts that deal with biological systems. So we tend to use the word catalyst just for chemical systems or chemical reactions, but then enzymes are something that we have in our own bodies that cause these reactions to either speed up or slow down again, or cause a reaction to products to form or products to break apart. So to throw the definition up here, a type of protein that speeds up metabolic reactions in plants and animals without being permanently changed or destroyed. So biological plants and animals fall under this biological topic or category. Each enzyme controls one reaction or one set of similar reactions, so enzymes are specific to the reaction that it's trying to control, either speed up or slow down. Most enzymes are fragile, and I'll modify this a little bit. They will stop working either above or below, so it doesn't have to be a hotter temperature, it could be a colder temperature where enzymes can stop working. Like in the human body, we're at 98.6 degrees. Typically enzymes are only going to function properly within a very small range from that 98.6, either a couple degrees above or a couple of degrees below. Outside that range, it's probably not going to work anymore. Substrate is the reactant in reactions catalyzed by the enzymes. So, for example, hydrogen peroxide is a substrate for catalase. Catalase is the enzyme. We throw the nice ASE at the end of enzyme, so whenever we say ASE at the end of a word, it's indicating that we have either a catalyst or an enzyme. So for this reaction, we've got hydrogen peroxide, which is this substance on the left. We put some catalase in there, it'll break down this hydrogen peroxide into water and the extra oxygen that's on there. So it just kicks that oxygen off. And we technically could write catalase on the end of this reaction as well. Alright, we've got equilibrium systems next. So what happens when a reaction goes backward as well as forward? So some processes may go in both directions, which results in an equilibrium system. So not all reactions just go one direction. These reactants react, you get your products. They can go from your products to your reactants. And we call this equilibrium. This can be described as the balance that is reached by two opposing processes. So some of these changes can be reversible. And if we were to write a chemical reaction out, we typically write a double arrow sign. This indicates the reaction can go in either direction. So an example here, a change of carbon dioxide dissolving. So carbon dioxide, CO2, we can get an increase in pressure and go from the gas above the liquid, increase the pressure, and then we can dissolve this carbon dioxide into liquid. So this is an example in soda. We've got the carbon dioxide that's within the soda. When you release the top by unscrewing the top, it gets released. So if we were to decrease the pressure, we can go back from gas dissolved in the liquid to gas above the liquid. And then we get this state of equilibrium when these rates balance. So when these forward reaction and the reverse reaction are equal, so that it's not, it's still moving back and forth, but it's a very small movement back and forth. So molecules of carbon dioxide are coming out of solution and dissolving back into the liquid at the same rate. So we see this in soda. We've got a bottle of carbonated water with the top on at equilibrium. So we do have carbon dioxide that's in the space above the liquid, carbon dioxide that's in the liquid itself. When the top's removed, carbonated water is no longer at equilibrium, so we do get more of a release of this carbon dioxide, so it tends to come out of the solution because you've released or have reduced the pressure on this system of this soda bottle.
When water is added to the tank on the left, the water moves from left to right. The level of water goes down a little on the left and up on the right. This is similar to adding more reactants to a reversible chemical system. The result is that more product forms because the forward reaction is favored until a new equilibrium is reached. We say the equilibrium has shifted to the right.
All right, so chemical equilibrium, the state of balance in which the rate of forward reaction equals the rate of reverse reaction and the concentrations of products and reactants remain unchanged. Systems in equilibrium respond to minimize change. We've got a special principle that we'll mention here. Le Chatelier's, it's French, Le Chatelier principle predicts changes in equilibrium. So given some different conditions here, starting with temperature, increasing temperature favors the reaction that absorbs energy. The condition is pressure. Increasing pressure favors the reaction that produces fewer molecules of gas. Concentration is the next condition. Increasing the concentration of one substance favors the reaction that produces less of that substance. So those are just some of Le Chatelier's assumptions. So Le Chatelier's principle: if a change is made to a system in chemical equilibrium, the equilibrium shifts to oppose the change, and then a new equilibrium is going to be reached. It can be used to control reactions, such as the Haber process. It's used to make ammonia. So we've got here nitrogen gas plus hydrogen gas under special conditions using Le Chatelier's principle to produce ammonia plus energy. So this product is not favored, so we have to change some of the surrounding some of that reaction to favor the production of ammonia. So most of this ammonia is produced when the reaction is run at a high pressure and a low temperature, so it requires those special conditions in order for the reaction to take place to produce that ammonia. Thanks for listening.